Turn to page 179. We've got increasing and decreasing functions and the first derivative test. All right, so we need to understand what increasing and decreasing means. And it means what you think it means, okay? So a function is increasing on an interval if for any two x coordinates, the x coordinate on the left leads you to a y coordinate that is less than the y coordinate on the right. Okay? Function's increasing. If you pick 2 points on the function, if the y coordinate on the left is smaller than the y coordinate on the right, then the function is increasing. And then vice versa for decreasing. A function is decreasing on an interval if for any two x coordinates, the x coordinate on the left gives you a y coordinate that's greater than the y coordinate on the right. Okay? If the y coordinate on the left is greater than the y coordinate on the right, then the function is decreasing. It works this way. A function is increasing if and only if its graph goes up to the right. Up to the right. That's what you expect increasing to mean, isn't it? And a function is decreasing if and only if its graph goes down to the right. And that down to the right is what you expect for something that's decreasing. Okay? So, increasing, if you know a function's increasing, then you conclude its graph goes up to the right. If you're told its graph goes up to the right, then you know it's increasing. Okay? If you're told a function is decreasing, you conclude the graph's going down to the right. If you see that the graph is going down to the right, you conclude the function is decreasing. It works the way you think it ought to work. All right? Now, here's something you need to know. This is big. F prime of x is positive if and only if f is increasing. Write that down. F prime of x is positive if and only if f is increasing. IFF means if and only if. Yep, that's a standard mathematical abbreviation for if and only if. Yep. So, I bet you can guess what the next sentence says. If f prime of x is negative if and only if f is decreasing. Something we already know, but I need to remind you of, because we just talked about here f prime being positive or f prime being negative. Well, f prime can also be 0. F prime of x equals 0 if and only if there's a horizontal tangent line. Let's think about that horizontal tangent line for just a minute. If there's a horizontal tangent line, the derivative's not positive, the derivative's not negative, that means the derivative or the function is not increasing, the function is not decreasing. Whenever you have the derivative equals 0, the function is not increasing at that point, the function is not decreasing at that point. Okay? All right, now, I just stated that when the derivative is positive, the function is increasing and vice versa, and you accepted it. Let me show you that it's true, okay? If we look at this graph right here, I'll show you the whole graph. If we look at this parabola right here, okay? The parabola is increasing for a while, then it has a relative maximum, or maybe even, if this is really a parabola, an absolute maximum, then it starts decreasing. Well, let's look. Over here, starting at the left, that represents a tangent line. Is the slope of that tangent line positive, negative, or 0? It's positive. And what is the graph of the function f doing right there at that tangent line? Increasing, decreasing, or neither? It's increasing. It's going up to the right. Same thing's happening here, isn't it? That tangent line has a positive slope, and the function is still increasing. And then look right here. That tangent line, well, I didn't draw the highlight very well, but the tangent line itself is horizontal. It has a slope of 0. And what's the function doing at 0 when the slope of the tangent line is 0? Is the function increasing right there? Nope. Is the function decreasing there? Nope. Does it surprise you that we have a maximum when the derivative equals 0? It shouldn't, because don't all maxes and mins occur at critical numbers? Okay? See how it's all hopefully fitting together? And then we keep moving to the right, and look here. Here we have another tangent line. What's the slope of that tangent line? Positive, negative, or 0? It's negative. And what's the graph of the function doing there? Increasing, decreasing, or neither? It's decreasing. Same thing there, isn't it? Okay? The derivative's negative. The function's decreasing. See how it works? And look. Trying to highlight. Just trying to further drill this into your head here. Let's start on this next parabola. Okay? First off, just tell me, look at the graph of f. Is f increasing or decreasing when we start off? It's decreasing. Then it has a, what kind of extreme value? Minimum, and then it starts increasing. So look what the derivative does. Derivative's negative, still negative. Derivative is 0 where the extreme value occurs. Derivative is positive. Derivative is positive. So what we're going to do is we're going to be able to figure out, without looking at the graph, where a function is increasing, where a function is decreasing. We know when it's increasing because the derivative is positive. We'll know when the function's decreasing because the derivative will be negative. And what happens when the derivative shifts from positive to negative? That's what happens over here. The derivative is positive, and then it's negative. What happens right there in between it being positive and it being negative? Derivative equals 0. We had a critical number. Now, I could have drawn it with a cusp, right? And I could have had a derivative does not exist. But one or the other has to happen, doesn't it? For the derivative to change signs from positive to negative, it has to either equal 0 in between or not exist in between. You have to have a critical number. And then same thing on the second parabola. The derivative starts off negative, hits 0, then it becomes positive, and that all coincides with the graph being decreasing, then having a minimum, and then increasing. So by knowing where a graph increases and where it decreases, we can figure out where the relative extrema are. We can find them all, okay, without ever seeing the graph. All right. Does that make sense to you? All right. The first example we're going to do is we do get to see the graph. So this is part of your assignment. This is number 6 on page 186. The directions are fairly simple. Identify the open intervals on which the function is increasing or decreasing. So we're going to list every interval where the function's doing the same thing. So we're going to find every interval where the function's increasing. We're going to find every interval where the function's decreasing. And you can do it that way if you want. Find where it's increasing, list those. Or what I usually do, I don't have to, I just start at the left and go across to the right, and I'll just write down, is it increasing, is it decreasing, which is it? So here's what I'm talking about. At first, our function is doing what? Increasing or decreasing? It's decreasing. So it's decreasing from negative infinity until, I don't know, looks like it's about 1, or negative 1, doesn't it? Okay, and look, it might not be. Maybe it's negative 1.1. I can't really tell for sure, but it sure looks like negative 1. So here's what I'm going to write. I'm going to write on the interval from negative 1 to, or from negative infinity to negative 1, our function is decreasing. And if you want to abbreviate decreasing as DEC, okay, just make sure you remember in your own notes what DEC stands for, right? And then when x equals negative 1, the function starts increasing again, doesn't it? So from negative 1 to something, our function's increasing. And what does that something appear to be? Sure looks like 0, doesn't it? So from negative 1 to 0, increasing. And then our graph is going down and to the right, so our function is decreasing again. So from 0 to about 1, so from 0 to 1, decreasing. And then increasing. So from 1 to infinity, increasing. All right. The first derivative test that I'm getting ready to show you takes this information that we figure out, where's the graph increasing or decreasing, and it does something special with it. Let's first look at the graph, then we'll ignore the graph and just look at our information. But look, we've got a derivative that's negative while the function is decreasing. Then we have a derivative that's positive while the function is increasing. And what happened there at that point where the derivative wasn't positive or negative? It was 0. And what happened when the derivative was 0? Right there. We had a relative minimum. When the derivative went from negative to positive, we had a relative minimum. When the graph went from decreasing to increasing, by definition, there's a relative minimum there. But looking at derivative, the derivative went from negative to positive. So at that point, that's in between the derivative being negative and the derivative being positive, we have a relative minimum. Then look at the next interval. So look at the yellow again. All right, we've got our derivative positive because the function's increasing. Then we've got the derivative negative because the function's decreasing. And what happens when x equals 0? The derivative is 0. And what happened there where the derivative is 0? Relative maximum, right? Relative max. When the derivative changed from increasing, when the function changed from increasing to decreasing, by definition, there's a relative maximum there. But when you look at the derivative, when the derivative changed signs from positive to negative, that point where it was 0, in between the derivative being positive and the derivative being negative, relative maximum. And then look what happens at the third place where the derivative changes sign. Okay? We had a max there, and we're back to having another min, aren't we? Because the derivative changed from negative to positive. All right, you with me? Graphically, we can pick that out. Okay? Now, didn't really do what I wanted it to do. Ignore the graph and just look at this. If our function is decreasing and then it goes to increasing, it's going down, then it's going up. What happened in between it going down and going up? Relative minimum. So at x equals -1, we can compute the relative minimum. Okay? And then here, our derivative, or our function goes from increasing to decreasing, from going up, then it switches to going down. When it switches from going up to going down, what's happening? A relative maximum. So, then increasing, it's back increasing, so it's going down, then it's going up. In between going down and going up is a relative minimum. Without even seeing the graph, we can conclude that, can't we? Okay? Now, what's the derivative when the function is decreasing, positive or negative? So instead of decreasing, what if I said f prime is negative? And I can mark it out there and say f prime is negative, right? And when the function's increasing, what do we know the sign of the derivative is? Positive. F prime is positive. F prime is positive. Now, well, let me write these intervals too. So from negative infinity to 1, infinity. And look what we figured out. I don't even have to know where the function's actually increasing or decreasing. I don't have to know that. I can figure all this out. If the derivative is positive, there's a relative change. If the derivative changes from positive to negative, what's the maximum at the x-coordinate where that change occurs? If it changes back from negative to positive again, there's another relative minimum at the x-coordinate where that change occurs. So you have to organize all this into a nice, neat little chart. But does the concept make sense? Any questions? Okay. All right. Here's the way the book writes the first derivative test. Test for increasing and decreasing functions. Test for increasing and decreasing functions. In the book, this is on page 179. It says let f be a function that is continuous and differentiable. If f prime of x is greater than 0, I would rather think of that as f prime of x is positive, then f is increasing. Hey, that's what we said. If f prime of x is less than 0, I think of that better as f prime of x is negative. If f is decreasing, that's what we said. If f prime of x equals 0 for all x, not just for one x, for all x in the interval, well, then you have a horizontal line. Okay? So f is a constant function. It's a horizontal line. Now, that happens, right? You have graphs that do that every now and then. That increase for a while, level off, and then you keep increasing. Maybe they increase, level off, and go back down. We actually use data to make graphs. That happens. Okay? Alright, so, like we've already said, if f prime is positive, f is increasing. If f prime is negative, f is decreasing. If the derivative changes sign from positive to negative or negative to positive, it must equal 0 in between being positive or not exist. Now, in the setup to this theorem, this is a theorem, so it's proven to be true. You don't have to rely on my words. You can take Newton's words. Okay? It's proven to be true. In this theorem, the function's always differentiable, which means the derivative always exists. But even if we expand that to where functions are not always differentiable, as long as they're continuous functions, then we can decide this. whenever the derivative changes sign, whenever the derivative changes sign, in between it changing sign, at the point where it's not positive or negative, it's neither one of those. Either it equals 0 or it does not exist. I mean, think about it. Pick any number in the world. Isn't it either positive, negative, 0, or not exist? It's your only choice, right? So if the derivative's not positive and the derivative's not negative, it's got to either be 0 or not exist. Does that make sense? See how this ties into critical numbers? Because critical numbers occur when the derivative equals 0 or the derivative does not exist. All right? So the derivative can only change signs at a critical number. And critical numbers are where all the relative extrema occur. Questions? All right. A term strictly monotonic. A function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. So a function that's always increasing is a strictly monotonic function. A function that's always decreasing is a strictly monotonic function. Okay? The phrase strictly monotonic, besides it being kind of awkward to say, simply means it's always doing whatever it's doing. Either it's always increasing or it's always decreasing. So this graph on the left here is the graph of a strictly monotonic function because that graph is always increasing. Now the one on the right, even though it never decreases, isn't a strictly monotonic function because it's constant there for a while. Okay? Well, it does have a derivative equals 0 right there, but when it's only for one little point, it's still increasing. Okay? Now, what we do to avoid this, and the reason our first derivative test is going to be helpful, is a continuous function can be divided up into intervals where it's strictly monotonic. Right? If we go back to this, well, that's messy looking now. If we go back to this graph here of this parabola is not strictly monotonic, but it is from negative infinity to whatever that x-coordinate is. It's strictly monotonic from negative infinity to c, and then isn't it strictly monotonic again from c to infinity? So we divide functions up into intervals so that they're either always increasing on that interval or always decreasing on that interval. Okay? And how do we divide our functions up into intervals? By finding the critical numbers. Because aren't the critical numbers the only places where the derivative changes sign? No. Yes. Yep. Y'all follow me on this? You want to see where I'm going with it, don't you? Well, I do too. All right. Here's the book's version of the first derivative test. It says, let C be a critical number of a function that is continuous on an open interval containing that C. If C is differentiable on the interval, except possibly at C. In other words, C is a critical number where either the derivative equals 0 or the derivative does not exist. But it's the only place in that interval where the derivative equals 0 or the derivative does not exist. Okay? The only place, the only critical number in that interval is C. Well, if f prime of x changes from negative to positive at C, all right, think here. F prime of x changes from negative, that's the function going down, to f prime of x being positive, that's the function going up. There has to be a relative minimum right there, doesn't there? Has to be. Because either the derivative is going to equal 0 to change, for the derivative to change from negative to positive, or the derivative is going to not exist for the derivative to change from negative to positive. And then just flip it all around for when the derivative changes from positive to negative at C. If the derivative is positive, the function's increasing. the derivative changes to negative, the function's decreasing. There's a relative max right there, isn't there? I'm finding extrema. I'm going to find extrema. Okay? Now, if we get a critical number, because we've always written, or we've always said that if an extreme value occurs, it occurs at a critical number. But not every critical number leads to an extreme value. So if you have a critical number, but the derivative is positive on both sides of that critical number, nothing happened. If the derivative is negative on both sides of that critical number, nothing happened. All that happened is like this, where you just had one little place there with the horizontal tangent line. That's all that happened. Okay? All right. Let's do a few. So, back to our assignment. Back to page 186. As you can see, we're going to do number 11. All right, on 11. The directions say, identify the open intervals on which the function is increasing or decreasing. And I'm going to go ahead and use this as an example of how to use the first derivative test to find relative extrema. Okay? So we're going to do what they say first, and then I'm going to show you how to continue this on and find the relative extrema. All right. G of x equals x squared minus 2x minus 8. If I'm supposed to find relative extrema, or I'm supposed to find intervals where the function's increasing or decreasing, I need the derivative. Because positive derivative means function's increasing, negative derivative means function's decreasing. So I need the derivative. Well, this is a fairly easy one. G prime of x equals 2x minus 2. I can factor that, so I'm gonna. If the question was just find the derivative, I wouldn't bother factoring this. But I've done just enough of these to realize what's coming is I'm going to get ready to say that critical numbers occur when the derivative equals 0 or the derivative does not exist. And if I had it factored, it's really easy to find where the derivative equals 0 or does not exist. Okay? So that's what we do. We write the magic sentence. Critical numbers occur when g prime of x equals 0 or g prime of x does not exist. Now look at our g prime of x. Is it ever going to not exist? It's a polynomial. It always exists. So you can go ahead and fill that part in. G prime of x exists. Now for the g prime of x equals 0 part, set the derivative equal to 0. And when you solve that, what does x equal? So that means that x equals 1 is the only critical number for this function. All right. That means that x equals 1 is the only place where the derivative can change sign. There's no guarantee the derivative is going to change sign, is there? But if it does, it has to occur at 1. So maybe the derivative is negative to the left of 1 and positive to the right of 1. Or maybe it's positive to the left and negative to the right. Well, let's find out. Here's the chart that we're going to use as our first derivative test. Now, I've seen very, very few other calculus students use this chart. That's because they didn't have me as their teacher. Because the first derivative test is more difficult for them than it's going to be for you. And I can take no credit for coming up with this chart. Some anonymous graduate student at the University of Kentucky in 1981 taught me this chart, and I've used it ever since. Here's what you put in this chart. I'm sure he actually had a name. I just didn't know what it was. Or at least I don't remember what it was. Okay? All right. In our table, we're going to have interval is our first column. K, which stands for constant, because, constant begins with less K. And it's just going to be a number we pick out that's in that interval. Then we're going to write down what the sign of the derivative equals. So sine of, in this case, g prime of x. Usually it's f prime of x. And then we're going to have a conclusion. And our conclusion is going to be whether or not our function is increasing or decreasing. Now, our interval. We want to write down intervals where our function is strictly monotonic on each interval. Since the only time the derivative can change sign is at x equals 0. Are we all clear on that's the only time the derivative can change sign? Okay? Because it can't change signs unless it's at a critical number. All right? Since that's the only time, that means our function is that means our function is strictly monotonic from negative infinity to 1, and again from 1 to infinity. I don't know if it's always increasing from negative infinity to 1 or always decreasing from negative infinity to 1, but I do know for a fact it's always one of those. It's always increasing or it's always decreasing. Because the only time a derivative, well, we worked it out, didn't we? The only time the derivative equals 0 is 1. The derivative always exists. So it's either positive or negative everywhere else, except for 1. Okay? Now, pick a number that's easy to work with that's in your interval. Whenever 0 is in an interval, that's the number I pick. So I'm going to pick 0 to be in my first interval, and then pick whatever positive number greater than 1 you want to pick. 10 works just fine. A million's good. Okay? All right, now, for that top interval, so I'm back up to, I'm on this line here. Okay? When k equals 0, so that's just a random x coordinate that I picked out that's in that interval. So when x equals 0, look at your first derivative. If I plug a 0 in there for x, is my first derivative positive or negative? It's negative. And this is another place where having your derivative factored is advantageous. I don't care what the value of the derivative is. I just care whether it's positive or negative. Okay? It's going to be negative. And if the derivative is negative, is our function increasing or decreasing? It's decreasing. So all I do is put negative, and then my conclusion is that f is decreasing. Now, just because it's negative in the first interval doesn't necessarily mean that it's positive in the second interval. I'm kind of thinking it probably is, but it doesn't mean it has to be. So I do have to do the test. So this time my test x coordinate is 10. So if I put a 10 there in the derivative for x, do I get a positive derivative or a negative derivative? I get positive, and then my conclusion is that f is increasing. Into the derivative. All right, I'm substituting 0 into the derivative, then I substituted 10 into the derivative. So that's all k stands for. It's a test x coordinate. Yeah. I made it up. I just picked a number that's in that interval. Because here's the thing you got to understand, and this is what we were trying to go over the first 15 minutes or so, is the derivative, the function must be either always increasing or always decreasing on this interval. Because the only time it can change from going up to going down is when the derivative equals 0 or the derivative does not exist. So I know that nowhere in that interval does it change. So just pick a number that's easy to work with, find what the sign of the derivative is, and that has to be the sign of the derivative for that entire interval. Because it can't change anywhere except x equals 1, which is when it equals 0. Make sense? All right, that's all the directions for this problem ask us to do. But I want us to go ahead and finish this off. If our derivative changes from negative to positive, which means our function went from decreasing to increasing, did we have a relative max at x equals 1 or a relative min? We had a relative min. Okay? The derivative's negative, so the function's going down. Then the derivative's positive, so the function's going up. Relative minimum. So I know for a fact there's a relative minimum. You don't have to write this down. I'm writing it down so you see it. Relative minimum at x equals 1. Right? We would, yeah, you probably can. Let's stick with relative. It's safer. Okay? All right, so what do we write down? So I've figured out that I'm going to have a relative minimum there. Remember now, the minimum and the maximum, for that matter, are actually the y coordinates on the graph. So when x equals 1, go to the original function, put a 1 in there, and tell me what you get. -9. I got -9. So there's just me working it out. G of 1 is 1 squared minus 2 minus 8, which is -9. So that means -9, which happens when x equals 1, means -9 is the relative minimum. Thus, I like it thus. G of 1 equals -9 is a relative minimum. You can put rel minimum. Fine. And that's how we use the first derivative test. So let's stop and think for a minute. It is. Yeah, -9 is the y coordinate for when x equals 1. What do you mean put it on the graph? We'll do that eventually, yes. I know this. I can sketch a graph of it. I know that when x equals 1, y equals -9, I know that my function is decreasing, then it's increasing. Now, I have no idea if it's a big, fat, wide parabola. You know, maybe it's not even a parabola. Maybe it's something else. But I know it looks basically like that. If it's not what? If the derivative equals 0, it changes the sign. Okay? Next example, number 33. And this time the directions are the whole shebang here. So this is everything we know how to do. Find the critical numbers, find the open intervals on which the function's increasing or decreasing, use the first derivative to find all the relative extrema, and I'll leave it to you to use your calculator to graph it and see if you get the same extreme values as you come up with on paper. Don't count on being able to do that on the test to figure them out. I may take your calculator away from you, okay? So, number 33, f of x equals x plus 1 over x. At this point in our lives, the easy part of the problem is supposed to be finding the derivative. So there it is. We can come back and talk about that when we have more time. So I want it as one fraction so that I can have a numerator and a denominator. It's very difficult to find where the function does not exist unless you have it as one fraction. Okay? To find where the derivative does not exist unless you have it as one fraction. So f prime of x equals x squared minus 1 over x squared. Then we use our magic sentence. Critical numbers occur when f prime of x equals 0 or f prime of x does not exist. if f prime of x equals 0, what equals 0? The numerator, x squared minus 1, which, by the way, I should have factored, shouldn't I? I just forgot to. So when x plus 1 times x minus 1 equals 0, and when f prime of x does not exist, what's that mean? The denominator equals 0. X squared equals 0. So, when the derivative equals 0, what two critical numbers do I come up with? 1 and negative 1. And when the derivative does not exist, what critical number do I come up with? 0. So all together then, negative 1, 0, and 1 are the critical numbers. So x equals negative 1, x equals 0, x equals 1 are critical numbers. And again, you don't have to line your critical numbers up from smallest to greatest, but I usually do because of what comes next. I need to make intervals, don't I? So in the first derivative test, I'm going to have interval for my first column, k for my second column, the sign of the derivative for my third, and then a conclusion for the fourth. As long as we're dealing with no closed intervals, they don't give us an artificial left boundary, you always start at negative infinity. So our first interval will be from negative infinity to negative 1. Then we'll go from negative 1 to 0, and then from 0 to, and then from 1 to, yeah, so we got 4 intervals this time. Negative infinity to negative 1. So negative infinity to the first critical number to the second one to the third one to infinity. As long as they don't give you a closed interval, start at negative infinity. All right. Now, here's where we're going to start getting different things, right? We may not all pick the same k. Why would we all pick the same k, right? I picked negative 10, negative 1/2, positive 1/2, and 10. Now, you can't use 0 as a test number here because since those are open intervals, 0 is not actually in there. And in fact, when x equals 0, we're going to get a does not exist for our derivative instead of a positive or a negative. Okay? All right. Y'all help me out with this. Let's go back to our derivative, and let's plug a negative 10 in here. Do we get a positive derivative or a negative derivative? Positive. We get a positive numerator, a positive denominator, positive. And since the derivative is positive, what's our conclusion? Increasing or decreasing? Increasing. Now, just because the first one's increasing doesn't mean it's going to go increasing, decreasing, increasing, decreasing. Let's see if it does. All right. When x equals negative 1/2, so if I put a negative 0.5 in here, what am I going to get? A positive or a negative derivative? It's going to be negative because the numerator is going to be negative this time, and the denominator is still going to be positive. So I'll get a negative derivative, and if I get a negative derivative, f is decreasing. I'm going to write it down in just a minute. So what happens at x equals negative 1, a max or a min? Increasing to decreasing. Max. There's going to be a max there. I'll figure out what it is in a minute. All right, when x equals positive 1/2, what's the sign of our derivative? It's negative again. We get a negative numerator and a positive denominator. So it's negative again. F is still decreasing. What kind of extreme value do we have at x equals 0? Yeah, we don't. We have none. because the function kept decreasing. All right? Then if I use positive 10 as my test number, now is my derivative positive or negative? Positive again, so f is increasing again. So here and here, I got a max. Here, I got nothing. Here to here, decreasing to increasing, I've got a min. Now, go back to the original function to find those values. I know that f of negative 1 is a maximum. I know that f of positive 1 is another relative, or is a relative minimum. So, go find them. Go back to the original function, plug in negative 1, you get a maximum of negative 2. Go back, plug in a positive 1, you get a minimum of positive 2. Boy, that doesn't make any sense, does it? I'll leave it up to you to make sense. Relative. Relative. Okay? All right. Besides the fact that you got to understand the max and the min thing, questions? All right. Now, here's something. The AP people, they don't like our conclusion column. They don't like it. And I used to really be frustrated at them for it, and I finally see their point of view. They want you to say as your justification that you have a maximum at negative 1, that the derivative changes from positive to negative. I was like, look, but since it changes from positive to negative, you get a maximum if your function changes from increasing to decreasing. And I'm right. But the function changes from increasing to decreasing, that's not really calculus to say that there was a maximum there, is there? All right, in Algebra 2, didn't y'all do some of that? Function's increasing, then it's decreasing, you called that the max. So, I like that column. I think it makes this make a lot more sense. On the AP test, your justification for that being a maximum is that the derivative changed from positive to negative. Because they're going to say that when you say that the function went from increasing to decreasing, they're going to say, well, honey, that's just the definition of a maximum, that it changes from increasing to decreasing. And I get their point. I don't really like it because I think you guys will understand it a little better than just memorizing positive to negative means max. I want you to understand it more than I want you to get that point on the AP test. But look, I also want you to get that point on the AP test. Okay, so y'all follow me? All right, let's try to get this last example in. Think about it, okay? Number 58. The graph of f is shown. Sketch a graph of the derivative of f. Okay, I can do that. Let's do that. So sketch that very quickly on your paper. We've done problems like this before, haven't we? Where I would give you f and say graph the derivative. So get f on your paper. All right. Our function is decreasing. When the function's decreasing, what's the sign of the derivative? Negative. So our derivative is negative. And then look, our function changes from decreasing to increasing. So right there, that's where the derivative equals 0, isn't it? So the derivative is negative, and then it equals 0 right there. And then what's our function doing? Increasing. So what's the sign of the derivative? Positive. And then it's positive that long, isn't it? So it's positive. And then what's our function doing? Decreasing. So what's the derivative? Negative. So the derivative's negative as long as the function is decreasing. Then what's the function doing? Increasing. So what's the sign of our derivative? And there we go. It's even easier now than it used to be. There's your assignment.